We want to find the center of mass of the solid S bounded by the paraboloid given by z equals 4x squared plus 4y squared in the plane z equals 7, and we're told to assume the density is constant. Let's first look at the solid S in space. The solid S is bounded by this red plane z equals 7 and the paraboloid graphed here in blue. So the solid is bounded below by the paraboloid and above by the plane z equals 7. More importantly, because this solid is symmetrical about the z-axis and it has constant density, the center of mass must be on the z-axis. If we recognize this, it's going to save us a lot of work because we know that the x and y coordinates of the center of mass will both be 0. If we look down on the xy plane, we can see the xy trace, or actually the z equals 7 trace, which would be this circle here, which is given by the equation 4x squared plus 4y squared equals 7. So going back to our work, again, if we recognize that x bar and y bar are both going to be 0 because the solid is symmetrical about the z-axis and it has constant density, it's going to save us quite a bit of work. We know x bar equals 0 and y bar equals 0. So the center of mass, again, is going to have an x-coordinate of 0 and a y-coordinate of 0, which means we only have to find the mass given by this triple integral and the moment about the xy plane given by this triple integral in order to find z bar. Let's first find the mass. So the mass m is equal to the triple integral, in our case, over the region S. The integrated function is rho of x comma y comma z, which is the density function, and we're told the density is constant, so we'll use the constant k for rho of x comma y comma z, and then we have differential v. But because the z equals 7 trace shown here, which we can see would be from substituting 7 for z, and therefore would give us the equation 4x squared plus 4y squared equals 7, because this is circular, it's going to be easier to evaluate this triple integral, so let's set this up using cylindrical coordinates. When converting from rectangular to cylindrical coordinates, remember differential v would be equal to r dz dr d theta. So the integrated function is kr, and then we have dz dr d theta. And now we need to find the limits of integration for z, r, and theta. Well, we know the solid is bounded below by the paraboloid, given by z equals 4x squared plus 4y squared, and above by z equals 7. But we need to write z as a function of r and theta, so let's go ahead and factor this equation here. We'd have 4 times the quantity x squared plus y squared. X squared plus y squared is equal to r squared. So we have z equals 4r squared, which is the lower limit of integration with respect to z, and z equals 7 is the upper limit of integration. So with respect to z, we integrate from 4r squared to 7. And now we'll use the z equals 7 trace of this trace here to determine the limits of integration for r and theta. To help us determine the radius of this circle here, let's go ahead and divide everything by 4. So if we have 4x squared plus 4y squared equals 7, and if we divide both sides by 4, notice how this tells us x squared plus y squared is equal to 7/4, which means r squared is equal to 7/4. Taking the square root of both sides of the equation, we know the radius r is equal to the square root of 7 divided by 2, which means the limits of integration for r are going to be from 0 to the square root of 7 divided by 2. And then for theta, we'll integrate from 0 radians all the way around the circle to 2 pi radians. So from 0 to 2 pi would be the limits of integration for theta. So this triple integral is going to give us the mass. So we first integrate with respect to z, treating k and r as constants. So the antiderivative is going to be krz. And now to find big F of b minus big F of a, we perform substitution for z. So when z is equal to 7, we have 7 kr minus, when z is equal to 4r squared, we're going to have 4r cubed k. Let's go ahead and write this as 4kr cubed. Integrating this back to r, we're going to have 7k times r squared divided by 2, or 7/2 kr squared, and then minus 4k times r to the fourth divided by 4, so we'll have just minus kr to the fourth. We now need to find big F of b minus big F of a, so we're going to have 7/2 k times, well, the square root of 7 divided by 2 squared is going to be 7/4, and then minus k times square root of 7 divided by 2 to the fourth, which would be 49/16. So this simplifies to the integral from 0 to 2 pi of 49/16 k. And now we integrate this back to theta. So we'll have 49/16 k times theta. So we'd have 49/16 k times 2 pi minus 0, which simplifies to 49 pi divided by 8k. So this is the mass, which we do need to find the center of mass, but we still have to find the moment about the xy plane given by m sub xy. So the moment about the xy plane is equal to the triple integral over the region S, and the integrated function is going to be z times rho of x comma y comma z, where again rho is a constant, so we'll have k times z differential v, and again we'll use cylindrical coordinates to evaluate this triple integral. So we'll have the triple integral. The integrated function is going to be k z r dz dr d theta, and limits of integration are going to be the same as the ones we use for the mass. So for z, we integrate from 4r squared to 7. For r, we integrate from 0 to the square root of 7 divided by 2. And for theta, we integrate from 0 to 2 pi. And now we integrate this back to z, treating k and r as constants. So we're going to have kr times z squared divided by 2, or 1/2 kr z squared. Now we need to find big F of b minus big F of a by performing substitution for z. So when z is 7, we're going to have 49/2 kr minus, when z equals 4r squared, we're going to have 1/2 kr times 16r to the fourth, which would be minus 8r to the fifth k. And now we integrate this back to r, treating k as a constant. So 49/2 times k times r to the second divided by 2, which is 49/4 kr squared minus 8k times r to the sixth divided by 6, which should be 8/6 kr to the sixth, or 4/3 kr to the sixth. Now we need to find big F of b minus big F of a. So when r is equal to square root of 7 divided by 2, this first term simplifies to 343 divided by 16k, and then we have minus, when r is equal to the square root of 7 divided by 2, this term simplifies to 343 divided by 48k, and of course when r equals 0, both terms would be 0. So this simplifies to the integral from 0 to 2 pi of 343 divided by 24k d theta. Integrating with respect to theta is just going to give us 343 divided by 24k theta. And now we need to find big F of B minus big F of A. So performing substitution for theta, which simplifies to 343 divided by 12 pi k. So now we know the moment about the xy plane. So we finally have all the information we need in order to find the center of mass. Going back to our first slide, we now know the mass is equal to 49 pi k divided by 8, and we also know the moment about the xy plane is equal to 343 pi k divided by 12, which means z bar is equal to the moment 343 pi k 12ths divided by the mass 49 pi k divided by 8. So this complex fraction is equivalent to the top fraction, 343 pi k 12ths, times the reciprocal of this fraction, which would be 8 divided by 49 pi k. Simplifying, pi divided by pi simplifies to 1, k divided by k simplifies to 1. 49 and 343 share a common factor of 49. There's 149 and 49, 7 49s and 343. 8 and 12 share a common factor of 4, 2 4s and 8, and 3 4s and 12. So the z-coordinate of the center of mass is 14/3. So you can see by recognizing that we had a constant density and symmetry about the z-axis, we saved quite a bit of work by recognizing that both the x and y coordinates of the center of mass would be 0. Otherwise, we'd still have to find the moment about the yz plane as well as the moment about the xz plane. I hope you found this helpful.